Hi, my name is Tomel. I used to work for an Israeli company you might have heard of called Wix, and yes, I know what that sounds like for most Central Europeans. A few years back, about 3 years ago, we built a flagship product called Wix ADI, and that is the basis of the story. Now, just for context, this was originally a talk designed for an Israeli audience. So Adi is a very common Israeli name, and we shall be meeting Adi in a minute. So everything I say is basically contextualized on that product, which you don't really need to know because I will explain. But the character is Adi, and this is the story of Adi. And yes, you're in the right room, so don't worry about it. This is Adi. Adi has a dream. Adi is a huge fan of a particular football or soccer for Americans team called Beitar Yerushalayim. It's a Jerusalem-based soccer team for whatever reason, and he is a rabid fan. And in his dream, every single person, every single one of his friends can go into a certain platform, a certain website builder, and produce a website for their particular favorite soccer team, in his case, Beitar Yerushalayim. Adi, not being content to just run a fan site, wants to produce a product, wants to produce a website builder that he obviously called after himself. So Adi sets out to design a website builder, and Adi is kind of a fashionable guy. So Adi does a lot of research, right? He goes to conferences, he reads blogs, he reads articles, he watches videos, he does his research, and he finds out that event sourcing is trending. And Adi, being a practical guy, does his research, agrees that event sourcing is the shit, and designs an event model. Now, if you think about it, when you build a website, the life cycle of a website basically consists of these 5 types of events, right? A website gets created, a website gets modified or updated, a website gets published. Like eventually you work in an editor, you build your website, you do your thing, and eventually you want to hit publish and see your website up in the air. Then eventually the website dies, right? Whether it's irrelevant, it's been replaced, the soccer group died, or maybe Adi just decided the soccer group is not for him. He ends up deleting the site, which we call archived because, as with most online services, we don't actually want to delete data. We just want to soft delete it or mark it as no longer relevant. And then, because oftentimes people make mistakes, right? You have your people building a website, or as in most of the people sitting in this room, in our case, we will be writing code, making a mistake. We want to revert to an older version. Therefore, we also have a restored event. So this is pretty straightforward. These are all the things that happen in the life cycle of a particular website. Now, having an event model is not enough. You need some way of codifying those events in a data store of some type. Now, Adi is, on the one hand, a fashionable guy, on the other hand, is a practical guy. So Adi chooses a traditional RDBMS, MySQL, Postgres, what have you, and designs a table schema to store those events. So each event that applies to a particular website has an ID, the ID of the site that the event pertains to. It has some timestamp, which we can use to order events, right? Event 1 happened before event 2, therefore it will have a timestamp that is less than that of event 2. And there's some metadata, right? The event type, some payload, right? If it's a modification event, it will have to include some sort of delta that the modification actually applies to the site. And here we go. We have a basic design for the storage subsystem of a website builder. Obviously, that is not the end of the story, because let me ask you this question. Put your hand in the air if you've ever run into this situation. You have a production system, it's been running for a while. You get a call or a notification of something, of a bug. You go into the system to start researching the bug. You end up looking at the data that's stored in your particular data store or brand of RDBMS. And looking at the data, you have this happen to you. The data does not make sense, right? No code path, no set of events happening in your system should be able to cause the data to arrive at the situation that it's in. The data is what you might call corrupted. Have you ever had that happen to you? All right, I saw about half the room raise their hands. Now, if you haven't raised your hand, you're one of three things. Either incredibly lucky, which I doubt, have never worked in a production system, which is a possibility, or are asleep, or lying, but let's assume you're not lying, right? Everyone I know has had that experience. Production systems always end up with data that just seems corrupt. Like you look at the data, it doesn't make sense. Nothing should have caused the data to arrive at the situation that it's in. It just sucks, right? And then you end up having to fix it, which sucks even worse. So, Adi is very confused because having those situations, having those bugs, having those notifications, he looks at the data and he sees that event streams in the database exhibit a number of pathological situations, like you get events coming in out of order. For instance, in this example, a site gets created, things happen, the site gets deleted or archived, and then you get an update event coming in after that. Now, by design, there's no situation in a D system that could cause this, and yet it happened anyway. You might get conflicting events. You might get impossible states for your event streams. All of these things happen in production systems all the time. And with those two things, right, that simple event model and storage model, and knowing that data ended up in a corrupt state, we can now start discussing how shit works, time. Now, time is a fickle concept. We as humans experience time in a very subjective way, but because it's such an innate human trait, we don't have to explain it to each other. If I speak to someone and I say, a while ago, I don't have to explain what time is. I don't have to have a mathematical model to represent time so that my conversation with my friend can make sense. On the other hand, as software engineers, we don't get to enjoy that sort of abstract way of having conversations. We have to have a mathematical model that we can use to model time so that we can reason about it in a computer system. So, what is time? Right? Let's go to a dictionary definition of time that you do not really have to read. I just want you to focus on the things that are highlighted there. Time is a system of sequential relations that is indefinite and continuous. The system is indefinite and continuous, right? Time doesn't end until the heat death of the universe, in which events succeed one another. So if we were to model this, if we were to design a model that computers can work with that represents time, generally speaking, every model of time in any computer system that you'd care to mention revolves around three things. The first of which is encoding, right? Time needs to be encoded. When you produce a timestamp, if you're working in Java, you might do system.currentTime millis. If you work in a different language, the API is different, but they all revolve around the same thing. You have an API that gives you back the current time in some sort of encoding that you can work with. Now, the most common encodings generally work like this. You have an epoch, which is the beginning of time, right? You have a timestamp, it's 0, right? You got a 64-bit integer that's 0 back from your API. That represents the beginning of time. The beginning of time has to map to some arbitrary but well-defined point in real time, the most famous of which is the Unix epoch, right? January 1st, 1970 at midnight, I think it's UTC, I might be wrong on that, right? That's an epoch. That's some arbitrarily selected point in time that by convention represents the epoch for a Unix timestamp. And then you have the timer resolution. Now, critically, these two things allow us to consider a single point in time. Right now, there's a timestamp. Right now, there's a different timestamp. Right? The difference between these two is that counting from the epoch with a particular timer resolution, we can represent instants in time as numbers. And in order to do that, we need to have some sort of timer resolution. The timer resolution, by the way, for most modern operating systems is 100 nanoseconds, which is a minuscule amount of time. Right? Human beings generally perceive time in increments of a few dozen, 20, 30, 50 milliseconds. That's sort of the human experience of the passage of time. Computers obviously are much faster, therefore the time resolution is much higher. Still, 100 nanoseconds is the resolution. What this tells us is if we have two events that happen to be within the same window of 100 nanoseconds, they will be mapped to the same timestamp. Right? If you call system.nanotime in Java twice, and you do that sufficiently quickly, eventually you will have two consecutive calls that give you back the same number. And this already gives us an indication of a problem in our model. Because however we produce the timestamps for the events in a D's system, right, the timestamps had to have come from somewhere. If two events happened or were recorded within that same 100 nanosecond window, they will have the same timestamp and therefore they will conflict. Right? That's already a problem. Now, given the asynchronous nature of computer networks, if you have a client sending a command to a server, right, that command ends up as a TCP, probably a TCP packet. It gets routed through various network appliances on the way. It does network hops, all of that stuff. It might be delayed. It might be lost. But what that tells you is that given a sufficient length of time in which your system runs and a sufficient number of events, you will inevitably reach a situation where two events conflict with each other in the sense that they both get assigned the same timestamp. So that's already busted. That's already broken. And that's just one problem that we can perceive with this representation of time. But let's move on, because this isn't all of it, right? This is just the beginning of how to model time in computer systems. So we have this encoding, right? We have an epoch, we have a timer resolution. We also need to bootstrap our clock somehow. A computer, or a CPU in this case, is a piece of machinery, right? It's this silicon chip. It doesn't have a brain. It doesn't have consciousness. It doesn't know anything. When you first run current through it, it does a lot of its internal bootstrapping. It resets the clock, but it has no clue what time it is. You need to tell it, as you woke up, dear CPU, this was the current time. This was the current real time that the humans around you perceived. And there are sort of three canonical ways of bootstrapping a computer clock. So if any of you are my age, give or take, grew up in the 80s, this should look pretty familiar to you, right? This is just an IBM PC or a clone booting up. And the first thing an 80s era IBM PC would do when you flip the switch is it would do a memory check, it would do the post, all that stuff, and then it would boot into DOS. And the first thing it does is it asks you to enter the time, because the original IBM PC and the original set of clones didn't have any way of saving the time between runs. As soon as you switch the computer off, it has no clue what time it is. Next time you switch it on, you have to type it in. Now, obviously, we don't do that anymore. We haven't been doing that for many, many, many years. The first thing that happened to improve on this is motherboards started including these batteries in order to back up the clock. These are called battery backed up clocks. Generally speaking, this is a battery that has a certain charge, and what it does is it just lets the CPU continue counting time, even when the computer is off, obviously. Now, we don't do that either anymore, right? No one has to set up their time manually in any of sort of modern day devices, iPhones, computers, whatnot. Nowadays, we use NTP. NTP seems like a panacea, a miracle cure. You just turn on your computer or your Android phone, whatever. It connects to your cellular provider. It goes to an NTP server somewhere, and it bootstraps its own clock. You don't have to worry about this as end users anymore. So these are the ways in which we bootstrap the clock. Finally, we need to update the clock. And this is what's called the system clock or the runtime clock. What's important to note is that there's some sort of clock signal. Generally, what you have is you have a crystal somewhere either on your motherboard or on your CPU that just emits a signal at a regular cadence, right? And your CPU takes in that signal and increases a counter. And that's all it is, right? There's a piece of silicon that just goes, okay, now, at a regular cadence, lets the CPU know that a certain amount of time had elapsed, and that certain amount of time is consistent. As we said, generally 100 nanoseconds. And this is where the problems really start creeping up, because although this seems to be a very simple system, the runtime clock actually isn't perfect. Clocks drift. Right? The fact of the matter is that that crystal oscillator that you have on your motherboard that gives out that update signal isn't that accurate. It seems to be very accurate, and it is if you think about it in the small. But it can actually be easily as much as 200 microseconds off of the perfectly synchronized timer signal that it needs to be. And no two oscillators are alike. What this means two things. The first thing it means is that if you set up your computer and you have on the one hand your computer and on the other hand you have a perfect clock. You have an atomic clock at home that's extremely accurate, that you know you can trust 100%. And you just leave those two, you synchronize them perfectly and you leave them running side by side. You go out for coffee, you come back, they're already out of sync. How much are they out of sync? Well, that depends on how much time had elapsed, because crucially, the drift, the error, the clock skew, there are multiple words for this, but clock drift is sort of the most common one, it accrues. It's cumulative, right? If you leave your system running long enough, that error starts adding up. And there are many, many different things that actually affect clock drift. If you take two machines that are identical, have the same motherboard, the same CPU, the same hardware, the same everything, you manage to synchronize the clocks perfectly and you just leave them running side by side, they will get out of sync. How much they get out of sync, again, depends on a lot of factors that you don't get to control. But critically, it means that you cannot trust any timestamp produced by two different systems, or even by one system over a span of time, to be fully consistent with each other and fully comparable. Right? And that's just an innate physical reality. Timestamps suck. This brings us to the problem of distributed time. Now, to tie this together to your sort of daily lives as software engineers. Let's say you have a system, right? You have these 4 clients that produce events, and they all send those events to a particular event stream that's stored on a particular event store. You have events coming out of those clients into the event stream. The question is, who produces the timestamp? Right? We said we mark down each event with a timestamp, and in an ideal reality, we should be able to simply compare the timestamps to know the ordering of events. Right? Event A happened before event B if its timestamp is less than that of event B. Right? But someone has to produce that timestamp. Someone has to make that system.nanotime or whatnot call in order to get that 64-bit integer and just stick it on the event. Who does that? So in this picture, you really have only 2 options. You can either do it at the client or at the data store, right? Because these are the actors you have in the system. Now, if you try to produce the timestamps via your application on the client, you very well might run into this problem, where because of clock skews, because the clocks are not absolutely and continuously synchronized with each other across all of these hosts, there can be subtle differences in the clock. You might get timestamps that don't actually reflect the event order. So you might actually end up with events in the store that are out of order. And again, that's just an innate physical reality of it. Now, here's the rub. You might think, okay, what if I perfectly synchronize my clocks? Well, there's 2 ways of doing that. One is, what if you use NTP, right? NTP is the Network Time Protocol. It's a very, very advanced piece of machinery that works really, really well for synchronizing clocks on over computer networks. It really works fantastically, right? That's the reason you don't have to worry about setting the time on your devices anymore. The problem with NTP is that if you, like the only viable number I could find was from a research paper from 2005. And that stated that generally the accuracy of NTP is up to within 10 milliseconds, right? And that's the best case scenario. If you have 4 hosts, you can expect at least 10 millisecond difference between their various clocks, right? Now let's assume the situation got better over the years. Let's say it's 1 millisecond. 1 millisecond is a lot of time for computers, right? We said we already mentioned that you can have event conflicts coming in with a 100 nanosecond resolution timer. It's inevitable. Now, if you take that up by 4 orders of magnitude in order to arrive at 1 millisecond, that's still way too much room for error. You will get events out of order. You will get event conflicts, right? So NTP is not a magical solution for this. More importantly, though, the fact of the matter is you can never actually fully synchronize clocks. Your network, the network that you're running on top of, is asynchronous. By definition, there are no synchronous networks. All networks are asynchronous. And it's been proven that you cannot have perfect failure detection on asynchronous networks. Therefore, you cannot actually rely on the fact that a network synchronization protocol will work perfectly in all situations. Okay, one of the ramifications is you cannot actually perfectly sync up a clock. You can get pretty close to it. You can get to a resolution where most systems would work fine, which is what Google does with Spanner. But generally speaking, most of us don't work for companies with the scale of Google. We don't have the engineering or the monetary resources to build something like Spanner. And it's super expensive. And most importantly, you don't actually need it because there are much easier ways of solving the problem that we have. So push comes to shove, you cannot actually generate timestamps from within your clients, from within the application, and then compare them. It just doesn't work. So you might say, what happens if I produce the timestamps from my data store, right? I have a single MySQL instance or whatnot. What happens if I generate the timestamps there? Well, there's 2 problems here. One is, as we said before, given the timer resolution and the async nature of the network you're on, it still doesn't work. It just does not work. Don't even go there. And more importantly, even if it did work, that would limit your data store to a single host, which for a lot of use cases is not good enough. It doesn't scale. There are availability issues involved in that. So that also is not really a solution to the problem. So TLDR version, dealing with time is hard. And you'll notice that at this point, I don't know what your expectations were, but if you thought I was going to be talking about time zones and leap seconds and all that stuff, I'm not even getting there. We're at such a fundamental level where you just have 2 timestamps and you want to compare them, and it turns out that you can't because generating timestamps doesn't work the way you think it does. So maybe we can reformulate the problem in a way that makes sense for us as software engineers and allows us to actually build the sort of systems we want. Let's go back to our dictionary definition of time. And I will repeat. Time is a system that is indefinite and continuous in which events succeed one another. Crucially, that last bit, in which events succeed one another, is where the solution to our dilemma lies. Let's consider, again, ADI, or Adi's website builder. Each site is an event stream. We have, for instance, this very, very simplified example. We have a site that gets created, it gets updated, and then it gets archived or deleted. And you'll notice that we have those timestamps. Now, from the point of view of your app, when you're reading in these events and building up an aggregate or a materialized view or a snapshot, right, whatever you want to call it, when you're reading data from the database and trying to reconstruct the sequence of events to make sense, you don't really care about dwell time. You don't care about it. The fact that a particular event happened on that date, May 3rd, 2017, at this hour or that hour, doesn't matter. It matters for purposes of bookkeeping. It matters for purposes of logging, of debugging. Maybe you want to display a timestamp to your user, but it doesn't matter in terms of computation. You don't care about that. What you do care about is the order of events. What's most important to you is that the events as written to the database can be read out in a way that's consistent, in a way that gives you a total ordering and is consistent across multiple hosts, multiple reads. This is what you want. So we don't care about timestamps. We care about order. And that particular statement is key to actually designing reliable systems in a distributed setting. In order to actually reframe the problem in a way that we can work with, we should consider what is an ordering of events. Right? What is the possible relationship between two events in a particular event stream? And it turns out events can have really only two types of relationships. We can have events that depend on other events. Events can happen before other events in a way where the second event cannot have occurred before the first one. So for instance, if you have a website, it has a creation event, it has an update event. Right? By definition, by the nature of your business domain, by the nature of your design, a site cannot be modified or updated before it was created. And it cannot be modified or updated after it had been deleted. So these are causally related events. This is a causality relationship. Happens before is sort of the academic formulation of it. But crucially, what happens before means is that given two events that where one happened before the other, it means there's a dependency. The ability of the second event to occur depends on the results of the first event having been processed. The other type of relationship you can have is concurrent, where you have these two events and they're totally unrelated. Right? This can happen, again, depending on your business context. In the case of a website editor, this can happen if two people concurrently edit a website but edit it in a way that does not correlate. If I edit a particular page, a friend of mine sitting a couple tables over edits a different page on the same site, those two edits don't have any relationship. Neither one happened before the other. It doesn't matter if the system of record says edit 1 happened before edit 2 or edit 2 happened before edit 1. It just doesn't matter. There is no causal relationship. These updates happen concurrently. But we still need a consistent way in which to order these events in our data store, otherwise we're not going to be able to reason about them. So, to reformulate the problem, here's what we need. This is what we're actually looking for. We need a versioning scheme for our events that respects causality, that is totally ordered, right? In which event A and event B have a number, I can compare that number. If the version for event A is smaller than the version for event B, then I can say with certainty that event A happened before event B in a consistent manner. And this versioning scheme must not rely on the runtime clock. It must not take into account all of that modeling of time that we just discussed, because I hope I got the message across, that doesn't work. What we want is an attribute that's called serializability. And if this sounds familiar, it's because if, as I assume most of you have built systems based on traditional RDBMS systems like MySQL, Postgres, SQL Server, Oracle, DB2, all of these systems are what's called ACID compliant. And crucially, ACID compliant systems give you, if you choose, generally that's sort of configurable at a transaction boundary, they give you various levels of consistency. And one of those levels is called serializability. That is the attribute of our system that we're interested in. And because we're building on top of a traditional database, that means we actually have a tool. We're already building on top of a tool that gives us what we need. We're just not using it correctly. So let's figure out what we can do to actually fix this broken system. And it turns out that it's a lot simpler than you might think. Let us consider the schema. right? This is the event storage schema that we started off with. We have a site ID. This event pertains to a particular site. We have the event time, that's a timestamp. We have the event type and a certain payload. The first thing we need to do is not to index or key on the timestamp. We need to stop taking the timestamp into consideration for queries or certainly for ordering, but generally speaking, timestamps are not reliable for any type of computation. You should still save the timestamp because it's useful for debugging and it's useful for user interfaces. It's useful for a bunch of stuff, just not for computation. So stop indexing, stop keying on timestamps. And then we need to add an explicit version field. Now, you'll remember that a versioning scheme has to support causality, and it has to give us something that we can compare between two events. Well, what's more natural than just a number, right? Event A, event B, version 3, version 4, therefore event A happened before event B. That's a very easy and natural way of expressing that relationship. So we add a version column to the database that's of some type integer, and we make that our part of our composite primary key. Now, let's see how we use that. Right? We have our system. We have our editor, that's like a web application or whatnot, that's the client, and it sends commands to the server. Now, if that terminology is confusing, then you should go and watch any of a million different talks about event sourcing and CQRS, and it'll make sense very quickly. But crucially, the client sends certain commands to the server, such as, here is my delta, please apply that to that site. Right? That's a command. So when you get a write command, what you do is you go to, in this case, MySQL, but any data store will do, read in the latest version, process your command, and generate the relevant events. On an update command, you might generate an updated event. So if the latest version is v0, then in memory, you produce events v1 through vn, v whatever. And you write all of these atomically. Now, when I say write atomically, it might sound like I'm talking about, open a transaction against your database and do everything within that. And you can do that for extra safety. But if you actually have one data store that's like an RDBMS, and you're using integers as your version numbers, you can just send a batch of ordered insert commands. Insert event 3, insert event 4, insert event 5, mash all these together into a single SQL statement, just send it off to the database. And the database will run those in sequence. Now, the first event, pardon, I'll circle back to that. Just produce the events, send them off to the database. Now, if you've succeeded, then you will have written events to the data store, and you have a version number you can then send to your client. Done. Right? I got a command, the version was 4, I added events 5, 6, and 7, they were written, done. Now the new version number is 7. On the other hand, you might get a primary key violation, because if the primary key is the composite of your entity ID, like the site, and a version number, then if you're at version 4 and you're trying to write version 5, and version 5 already exists in the database, that essentially means you have two racing updates. Right? You have two clients that are trying to write, or that are issuing commands to the server. You have two threads on the server trying to write the same event to the database, the same event version. And those two threads are racing. One of them will succeed. The event number 5 will have been written to the database. Cool. The other one will fail with a primary key violation. Now, the nice thing about that is that this primary key violation actually gives you all the data you need to know that you have a race. And it gives you the opportunity to do something about it. And you can do one of 3 things. Option 1, you retry. Right? If your business domain allows it, if your command is one that is quote unquote stateless or idempotent, let's say it's a delete command, right? Let's say you have 2 editor windows open. In one you make an update to the site, on the other you delete the site. Why would you do that? I don't know, but users are weird, they might try it out. right? And the update succeeded before the delete. Well, delete is idempotent. It doesn't matter which version you started off with when the site was marked for deletion. So you can try and emit that event, get a primary key violation, and then you can just retry. You can recreate the event with a higher version number based on the event tail that you missed, and just retry. And that's effectively a spin lock. Option number 2 is you can propagate that error to the client. So in the case of Wix ADI, which is the product we started this whole story from, Wix ADI, as a conscious product decision, does not allow for concurrent editing. Our customers back then are unsophisticated. They don't run teams. They just do stuff on their sites alone. We don't allow multiple editing sessions, right? So if, for whatever reason, a client ended up in a situation where they do have 2 separate sessions of the editor running against the website, and both sessions are trying to produce an update, those updates obviously conflict, and we don't allow this. We just we race the 2 updates. The one that failed pops up a message. That error is propagated to the client, which pops up a message saying, look, you have 2 editor sessions. I don't know how you managed to do that, because we have a bunch of mechanisms to prevent you from doing that, but you managed somehow. Sorry, you're going to have to edit this session. We don't support this. We don't know how to manage this. And if you've had the experience of trying to, say, start, I don't know if WhatsApp is like a commonplace thing here. Does anyone here use WhatsApp? Yeah, sufficient. If you've tried opening the WhatsApp web client, and you tried opening multiple tabs of it, or opening the web client for WhatsApp on multiple computers, it will tell you that you cannot actually have multiple WhatsApp windows open at the same time. So it's the same experience. And from a product perspective, that's perfectly viable for certain types of products. And this mechanism just let us do that, right? If we have that primary key violation, we propagate it to the client, and we just say, sorry, no can do. And that's a product decision you can now make. Or if your business allows it, your business domain requires it, and it makes sense, what you can actually do is say, I have the command that failed the race. I have new events that have been written to the data store. I can actually query those, get those into the server, and do some sort of smart merge. I can actually reapply that command, if it makes sense, based on the new events that happened concurrently while I was doing my processing. Right? That's something you can do. For a website editor, that means, or a text editor for that matter, that means you can actually take both modifications and apply them to the same site, and just produce the new events and rewrite them and write them again to the database. So you have that option. And it's a very pleasant design to work with, because it means that once you stop relying on the timestamp, once you start relying on consecutive version numbers, you can no longer get into a situation where events come in out of order. So that's what you can do to fix a very, very common mistake in an event source system if you're working on top of MySQL. Now, this is sort of, I mean, on the one hand, great success. We have managed to fix this particular product. There are many, many products in which this solution will not fly for a simple reason, which is you'll notice that here I have an ACID-compliant database which serializes all the writes. Like, all of the writes go through that same data store. If you have multiple data stores, which can happen if, for instance, you have a clustered data store, or you have replication, or you have a leaderless data store. If you don't have that single source of truth that all writes go through, then you need to employ other techniques. Those techniques are quite a bit different and quite a bit more either convoluted or complicated to implement. But again, it's engineering. There's no magic here. So I don't actually think we have the time to go into that, which is a bonus section. So I'll just give you the TLDR version. If you have multiple data stores, or you have a replicated, charted, clustered data store, means you have multiple hosts, which means you can't rely on primary key violations to tell you when you have a race, then there's a host of other techniques you can use. And the first technique you should look into is LAMP or timestamps, which unfortunately I don't have enough time to go into, so I'm going to skip all of this. But that's a set of techniques you can start looking into, and actually it's the same set of techniques that modern NoSQL type data stores employ, right? So if you've used Riak uses dotted version vectors, which is a different technique to vector clocks. It's a deep rabbit hole to go down, but you don't really need to go down that rabbit hole unless you do something, I don't know, I would say relatively advanced. The key takeaway here is don't use timestamps for ordering and versioning. Time is hard. Time representations in computer systems are more complicated than you think, and it's very, very easy to get them wrong. So just don't use them. Okay, figure out what problem you're trying to solve, minimize the surface area of the problem you're trying to solve to the simplest components possible. Generally speaking, if you use timestamps for ordering, it means you're using the wrong tool because you're trying to solve the wrong problem. What you want is not time. What you want is ordering. And that is unfortunately a pretty common mistake that I've seen made. And I hope after this, you will no longer make it. Before we go on to questions, if there are any, if my model can have a round of applause. This is Kfil, a colleague of mine, and he worked very hard for these pictures. So thank you, Kfil. And with that, I think we have a bit of time, and there's no one here to tell me that I'm wrong. So if there are any questions, I'd be more than happy to take them. And if not, then you're more than welcome to catch me today or tomorrow at the conference. Thank you very much. Any questions? Nope? Okay, enjoy the conference. Thank you.